the universe had an order. According to cosmology, everything was supposed to form slowly, a calm symphony spanning 13.8 billion years. But we were wrong, terribly wrong. James Webb looked to the very beginning of time and shattered everything we knew. Just 300 million years after the Big Bang, it found galaxies that were impossible to form in less than 2 billion years. These galaxies were massive because they held hundreds of billions of solar masses. They were also chemically rich, meaning multiple generations of stars had already lived and died within them. But that wasn't the most terrifying part. This discovery shows that the universe's fundamental dark matter model might be completely wrong. If you too are curious about how the most fundamental laws of the universe are being shaken, then like this video and subscribe to the channel. Because you are about to witness the collapse of everything cosmology thought it knew. Are you ready? Here we go. The universe was supposed to make sense. We had our equations, our models, our timelines. We knew how galaxies formed and how long it took. But then the James Webb Space Telescope launched, and within a few months, almost everything changed. Webb looked back to just a few 100 million years after the Big Bang. It found galaxies there that shouldn't have had the time to exist. Massive, novel, well-structured, and chemically complex galaxies. They were forming stars at rates that no model had predicted, but because this telescope was built to look into the farthest corners of the universe. It's the most powerful space telescope humanity has ever made. It took over 20 years to build. It cost roughly $10 billion. This giant eye operates about 1.5 million kilometers away from us. It is shielded from the heat of the Earth and the Sun by a sun shield the size of a tennis court. So, it can operate in freezing temperatures like -233 degrees Celsius. But that is not its true power. Its real power is hidden in the type of light it observes. Webb primarily operates in infrared light. This light is the stretched out, redshifted version of visible light, coming from the most distant objects in the universe. Imagine drawing a wave on a rubber band, and then stretching that band. The wavelength gets longer. The universe does exactly that to light. The farther away an object is, the more its light gets stretched during its journey. Previous telescopes like Hubble could not see this stretched light efficiently, but Webb was designed precisely to capture this very light. Because its massive 6.5-meter mirror is made of 18 gold-plated hexagonal segments of beryllium. This sensitivity allowed it to look at a patch of sky that previously seemed dark and find thousands of galaxies there. This was a capability we had never had before. This ability didn't just mean seeing farther, it meant testing the most fundamental rules of the universe. So, when Webb looked into those seemingly empty voids, scientists were shocked. They expected to find galaxies there, but the shapes of the galaxies they found were the problem. These galaxies had the smooth or organized appearance of galaxies that had been forming stars for billions of years. They had disk structures. Some even showed hints of spiral arms. According to standard cosmology, developing such complex architecture should have required at least 1 to 2 billion years to pass after the Big Bang. But these galaxies seem to be sitting at distances corresponding to the first few 100 million years of the universe. On the cosmic clock, there wasn't enough time for them to look this way. One astronomer likened the experience to opening a box that should contain raw ingredients, success and finding a fully cooked meal. This analogy was spot on. Because the models said that in the universe's early days, galaxies should have been small, irregular, and faint. What Webb found was the exact opposite. They were bright, large, and surprisingly mature. This situation initially led scientists to suspect an instrument error. They double-checked the data. They reran the calibration. But every time, the images came back clean. The anomaly was not in the telescope. It was in the universe itself. But the truly shattering blow had not yet arrived. These discoveries were a mix of exciting and worrying, but perhaps they could be somehow incorporated into existing models. However, a paper published in early 2023 eliminated that possibility. Researchers announced they had found 6 massive galaxies in Webb's initial data. These were not whispers buried in noise. They were bright, clearly resolved, and very old objects. Their light placed them firmly within the first 700 million years of the universe. One of these galaxies had a mass roughly 100 billion times that of our Sun. These numbers were checked again and again. They were reanalyzed by different teams. And yet, the result did not change. Because these 6 galaxies shattered something very well known in cosmology. It's called the stellar mass function. This function describes how much mass you should expect to find in stars at any given point in cosmic history. It's not a guess. It's a precise mathematical prediction, calculated from basic physics, from how fast gravity collapses gas, and how long the universe has been expanding. And these 6 galaxies violated that function so violently that one of the paper's lead authors likened the situation to finding dinosaurs in the Precambrian era. This metaphor was chosen carefully, but because this wasn't just something unexpected. This was structurally incompatible with the timeline. These objects simply should not have been there. Science has established processes for dealing with anomalies, but these anomalies survived every check. The galaxies were real, their masses were huge, and their ages were impossible. This created a rift in the scientific community. Some researchers argued that we could explain these results by stretching the current model a bit. Maybe star formation in the early universe was far more efficient than we thought. But others said that stretching a model that much isn't the same as explaining. If a model requires such special pleading, then the model itself needed to be examined more critically. This was only the beginning, because the mass and age problem of these galaxies pointed to a much more fundamental issue. Hidden within the data, the question of what built these galaxies so quickly would lead scientists to a place they never expected. Because what these stars produced wasn't just light. It was also, and it wasn't just light, it was chemistry. The chemistry that would write the entire future of the universe. Because these impossible galaxies weren't just too big and too early. They were also chemically far more complex than they should have been. This forced scientists to reconsider the most basic biography of the universe. And what was written in that biography was a much faster story than the models had told. Because the universe has a history. This history is written in elements. In the first few minutes after the Big Bang, the universe produced only 2 elements, hydrogen and helium. That's it. But when you look around you today, the situation is different. Because the oxygen you breathe, the calcium in your bones, the iron in your blood, None of this existed at the beginning. Every single element, heavier than helium, had to be forged in the nuclear furnaces at the heart of stars. When these stars died at the end of their lives, they exploded, scattering these new elements into space. So, the next generation of stars formed from this chemically enriched material. Each cycle increased the chemical complexity of the cosmos. But this process has a speed we can calculate. And yet, Webb showed that this speed was completely wrong. In one observation, oxygen was found in a galaxy from just 500 million years after the Big Bang. According to standard models of stellar evolution, it should have taken at least twice as much time to accumulate this amount of oxygen. This was like a baby running a marathon a few hours after being born. This situation gave rise to the hypothesis that the first generation of stars might have been much larger and more energetic than we thought. But this chemical chaos was not the only anomaly Webb found, because a much larger, much darker monster was lurking in the centers of galaxies. This monster was a supermassive black hole. Almost every large galaxy in the observable universe has one at its center. In the center of our own galaxy, much as the Milky Way, there is a black hole named Sagittarius AA, with a mass about 4 million times that of the Sun. These giant objects were thought to grow on billion-year timescales by swallowing the gas and dust around them, and occasionally merging with other black holes. This model makes a very simple prediction. In the very early universe, there should not be massive black holes, because the seeds have not had enough time to grow. But Webb found one. In 2023, a team using Webb data detected a black hole with a mass of several million to tens of millions of times that of the Sun. The host galaxy of this black hole placed it less than 1 billion years after the Big Bang. How is this possible? Because there is a physical limit to how fast a black hole can feed, like it's called the Eddington limit. If it tries to feed too quickly, the radiation it emits pushes back on the incoming material, slowing down the feeding. For this black hole to reach this mass in such a short time, it would have had to be feeding at almost the full physical limit, that is, every single day of its existence. This is like eating non-stop, at the maximum speed physics allows. This suggests that either the seeds were much larger than we thought, or the early universe created feeding conditions that standard models do not include. Both options required new physics, but the problems didn't end there, because the universe itself went through a period in its history known as the Dark Ages. About 400,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine and form neutral hydrogen atoms. Before that moment, it was a hot, opaque plasma through which light could not travel freely. After that moment, space became transparent. However, this transparency was not permanent. For hundreds of millions of years, the universe became a place without stars or galaxies, with only dark clouds of neutral hydrogen gas slowly condensing in the darkness. Then, the first stars and galaxies ignited, and their intense ultraviolet radiation began to tear apart these neutral hydrogen atoms again. This process is called reionization, and it cleared the universe of the fog that had permanently enveloped it. The standard model predicted this process would be relatively smooth and gradual, like a wave of enlightenment slowly advancing throughout the universe. But Webb's data painted a completely different, much more chaotic picture. In some regions of the sky, traces of neutral hydrogen had lingered much longer than expected. In others, the gas appeared to have been cleared at an incredibly early date. This patchy nature of rionization was far more extreme than any leading model had predicted. This meant that different regions of the universe were evolving at different rates, and those different rates were feeding a tension that had been quietly building in cosmology for years. So, what do we have? Galaxies growing too fast, chemical elements forming billions of years early, giant black holes that shouldn't have had time to grow, and a universe that lit up in a much more chaotic way than expected. These concepts show how deep the problem is, but these are just theoretical frameworks. What did the actual images, the real data coming from Webb's camera, say? What exactly was seen in that first deep field photo? Because the real reason for that deep silence in the control rooms was more than just these theoretical problems. The reason for that silence was what the telescope saw. And now comes the real shock. Because what the telescope saw was much more than a theoretical problem. It was a photograph, a piece of evidence, a portrait of thousands of galaxies, crammed into a patch of sky smaller than a grain of sand. But this portrait was about to demolish our most fundamental beliefs about the universe. Here are the real findings that plunged the control rooms into that heavy silence. Here is the pattern that scientists feared. It all began with that first deep field photo released on July 12th, 2022. Hubble had taken deep field photos before. But Webb's image was different, immediately, uncomfortably different. Because, in Hubble's images, the oldest and most distant galaxies appeared small, faint, yes, and irregular. They looked young. They looked primitive, exactly as a very young galaxy in a very young universe should look. But in Webb's image, those ancient galaxies looked nothing like what the models predicted. Most were bright. Some had clearly organized structures. One stood out near the edge of the image, and it was studied in detail with follow-up work. This galaxy seemed to contain a mass equivalent to hundreds of billions of times that of our Sun. That means a large, lachi, fully developed galaxy by any standard. But the light from this object showed it as it was just roughly 300 million years after the Big Bang. Standard models said this was physically impossible. You cannot build something that big in that short time. There wasn't enough time for gravity to gather that much matter, to compress it, to ignite the stars, and to produce the chemical complexity that Webb detected. The reaction in the scientific community was a mix of genuine excitement and a feeling closer to alarm. Because this wasn't just one image. This was the first sign of a pattern. But the real problem wasn't just those distant galaxies themselves. The problem was time itself. The universe has an age, about 13.8 billion years. This is one of the most precisely measured numbers in science. So, what's the problem? When the age of some of the oldest stars orbiting our own galaxy is calculated, the results are close to 13.2 billion years. This leaves an extremely narrow window of only about 600 million years between the Big Bang and the formation of those stars. But Webb was finding evidence that those distant galaxies, when the universe was 500 million years old, had already been going through star cycles for hundreds of millions of years. Think of it this way. You're told a house was built in 1980. You go inside and find antique furniture from 100 years before that date. The house might still have been built in 1980, But the story of how the furniture got there requires a new explanation. The universe might still be 13.8 billion years old. But what the age problem questions is the timeline of what happened within that age. The speed at which matter organized, stars ignited and died, seems significantly faster than the models allow. So, the speed of cosmic history is the backbone of the entire discipline, and that backbone was under serious pressure. And then that paper was published in early 2023, and everything got worse. A research team published a paper identifying 6 massive galaxies found in Webb's early observation data. These were not faint hints. They were bright, clear, and old. Their light placed them definitively in the first 700 million years of the universe. One of them had a mass of about 100 billion times that of our Sun. These figures broke a very well-established concept in cosmology known as the stellar mass function. This function is a precise mathematical prediction derived from fundamental physics. But these 6 galaxies violated that function so violently that one of the paper's authors likened the situation to finding dinosaurs in the Precambrian era. This metaphor was not random. It wasn't just unexpected. It was structurally incompatible with the timeline. The technical term was candidates for extremely early galaxy formation. But the living translation behind this technical language was simpler. They should not have been there. Scientists checked everything. The instruments, the alternative explanations. But the objects remained. The crack had become too wide to ignore. So, what did we have? Galaxies that matured billions of years earlier than expected. A timeline that contradicted itself, and cosmic dinosaurs that didn't fit the geological timescale. These were not singular errors. This was a pattern. A consistent pattern found again and again by independent groups. And this pattern was forcing scientists to look into one of the darkest corners of their models. Because there had to be a common cause underlying all these anomalies. There had to be an invisible mechanism that built these galaxies so fast, that enriched them so early. But, while searching for this mechanism, Webb noticed a much larger structure, a massive, invisible web connecting the galaxies. And that web was warped. The cosmic web, the largest structure in the universe, a giant filaments of dark matter and gas, stretching for billions of light years, connecting clusters of galaxies. The standard model says this structure grows slowly over time, hierarchically. Small structures form first, then they merge to form larger ones. So, in the early universe, this web should have been only in its infancy. Thin, fragile threads, barely defined clusters. But Webb looked, and it found a structure that shouldn't have been there, at a distance corresponding to just 400 million years after the Big Bang. It detected what appeared to be a protocluster. This was the early stage of a large galaxy cluster, but at that date, in 400 million years. The universe shouldn't have had time to gather so many galaxies into one dense region. This was like watching a fully paved city emerge in a place that should have been empty land for another billion years. The city's existence is not impossible in principle, but the speed of its construction was breaking the rules. This suggested that Webb was witnessing a process that skipped steps in the hierarchical merger model, or compressed them into timescales that had no explanation in the current model, because outliers, the only thing that could cause this acceleration was the behavior of dark matter itself. But this wasn't just an accelerating structure, it was also a structure that was rapidly producing stars. Because models don't just say when galaxies form, but also how fast they can produce stars. Star formation has a physical speed limit. But Webb's data showed that galaxies in the early universe were producing stars at rates that seemed to exceed these known physical limits. A galaxy observed in the first billion years of cosmic time was forming stars at a much higher rate than any model predicted for an object of its size. Let's put this into perspective. Our own Milky Way galaxy today forms roughly 1 to 2 new stars per year. Some starburst galaxies can form stars at hundreds of times that rate. But these events are extreme, short-lived walks, and occur in much later epochs of the universe. To find something similar happening routinely at distances where the universe had existed for less than 10% of its current age was profoundly inconsistent with the current framework. Theorists suggested that the early universe might have had fundamentally different conditions than we assumed. Perhaps a mechanism was allowing gravity to work at speeds we hadn't accounted for. So, what was really keeping scientists awake at night wasn't just the star formation rate. It was what those stars were doing to the space around them. And there was water. Finding water in the earliest epochs of the universe is not something you expect. Because the molecules that form water require specific conditions to form, and more importantly, to survive. In the extremely energetic, radiation-filled environments of the earliest galaxies, molecular bonds are constantly broken and reformed. But Webb's infrared spectroscopy is sensitive enough to detect molecular signatures at vast distances, and it found evidence of water vapor in galaxies much farther away, and therefore much older than previous instruments could study. The significance of this is multi-layered. At the most basic level, the formation of water requires oxygen. Oxygen is a heavier element produced only by stars. So, finding water signatures at high distances is another chemical fingerprint of advanced stellar processing that happened early. But on a second level, the spatial distribution of the water detections is also informative. They tend to be clustered in regions associated with intense star formation activity. This suggests that the link between stellar processes and complex molecular chemistry was already established in the early universe, long before the timeline described by the models. And now the organic chemistry data came in, and this data made the water discovery seem almost mundane. Polyaromatic hydrocarbons. These are a category of organic compounds that form on the surfaces of dust grains floating in interstellar space. Webb detected signatures consistent with this category of molecules in galaxies at distances that placed them in an era when the universe was only a few billion years old. This implies that the chemical enrichment in organic compounds was proceeding at a significantly faster pace than any current model predicted. So, this is the picture we have. Prematurely mature galaxies, masses that look like dinosaurs, a warped cosmic web, star formation rates exceeding physical limits, and water and organic chemistry in unexpected places. These discoveries are interconnected. They all point in the same direction. The early universe was not the quiet Pashtash-Kamij, slow nursery described by the models. Something was happening there that the models had completely failed to predict. So, how does this mechanism work? What is the engine itself that built these galaxies so quickly? What is the role of dark matter? To find the answers to these questions, we now need to dive into the physics behind these discoveries, the technical details of that engine, because in those details lies the key. not just to these anomalies, but to the future of the universe itself. But how does this engine work? What is the physical mechanism behind so many anomalies appearing all at once? The shocking discoveries we've seen so far are only the surface of the story. But beneath that surface lies a deep and technical debate about the fundamental workings of the universe. So, let's slow down the tempo for a moment, and let's take a closer look at the fundamental mechanisms that make these anomalies possible. The parts of the engine that Webb has shown us. Because the answers are hidden in those technical details. First of all, the reason Webb is so revolutionary lies in how it captures a phenomenon we call redshift. Think of it like the siren of an ambulance coming towards you. As the ambulance approaches, the pitch of the sound gets higher, and as it moves away, it gets lower. Because the sound waves are being compressed or stretched. Light is also a wave, and because the universe is expanding, distant galaxies are constantly moving away from us. So, the light coming from them is stretched, just like the siren of the receding ambulance, and its wavelength gets longer. This stretching shifts the light towards the red end of the electromagnetic spectrum, and even beyond visible light, that is, into the infrared. The farther a galaxy is, the faster it moves away from us. So, its light is redshifted even more. Webb was designed precisely to capture this extremely stretched, chopped ancient light. While telescopes like Hubble can mostly see wavelengths between 0.2 and 2.4 microns, Webb's instruments like NIRCam and MIRI cover a much broader infrared range, ICAS, starting from 0.6 microns and extending all the way to 28 microns. This is like a window opening onto a universe where Hubble was blind. Webb can see objects that are about 10 to 100 times fainter than what Hubble could see. This sensitivity allows it to see not just farther, but also earlier. Because, since light takes billions of years to reach us, when we look at a galaxy 13 billion light years away, we see it as it was 13 billion years ago. So, Webb is essentially a time machine, and the first things that machines saw made us question everything we knew about time itself. But Webb's secret is not just seeing infrared light, it's also how it analyzes that light. The key to this analysis is a phenomenon called gravitational lensing. Einstein's theory of general relativity says that mass bends space-time, just like a heavy bowling ball placed on a stretched rubber sheet. Now, if you roll a marble across that sheet, the marble's path is bent by the curve created by the bowling ball. Light behaves the same way. A massive galaxy cluster that happens to be between our world and a very distant galaxy acts like that bowling ball. It bends, magnifies, and sometimes even creates multiple images of the light from the more distant galaxy behind it. This is a giant telescope that nature provides for us. Webb uses these natural telescopes in an unprecedented way. The power of this lensing can amplify the light of the object behind it by hundreds, even thousands of times. This allows Webb to detect galaxies that are so faint and distant that it would never be able to see them otherwise. But the real power of this mechanism is not just magnification. The way and amount the lensed light is bent gives us incredibly precise information about the total mass of the intervening galaxy cluster. And this mass is much more than the visible stars and gas. The difference is dark matter. So, by using gravitational lensing, Webb not only sees distant galaxies, but it also maps the invisible skeleton of the universe, the distribution of dark matter. And those maps started to differ from what the models predicted. In some clusters, the dark matter seemed to be more densely concentrated at the center than the models allowed. In others, it was distributed a bit more smoothly. These inconsistencies provided the first clues that the mechanism accelerating early galaxy formation might be dark matter itself. These two powerful mechanisms, redshift and gravitational lensing, tell Webb what to look at. But the real magic that allows it to understand what it sees is spectroscopy. The total light from a galaxy tells you how bright it is. But if you pass that light through a prism and separate it into its colors, that is, take a spectrum, you learn so much more. Because different chemical elements absorb or emit light at very specific wavelengths. This is like each element leaving its own unique fingerprint. Reading a galaxy's spectrum is like reading the chemical history of every star that has lived and died within it. Hydrogen, helium, oxygen, carbon, they all leave their own signatures in the spectrum. Webb, hers, with its instruments like NIRSpec and MIRI, is doing something that was previously impossible. It can take detailed spectra of even incredibly faint, thus distant galaxies. It achieves this thanks to a technology called the microshutter array, which can take spectra of hundreds of different objects simultaneously. This is a system of 250,000 miniature shutters, each thinner than a human hair. These shutters can be opened individually, allowing Webb to analyze the light of only the objects it's interested in. Thanks to this efficiency, Webb can do a job in hours that would take Hubble weeks. So, when it found oxygen signatures in a galaxy from just 500 million years after the Big Bang, this was not a guess. This was a reading of that galaxy's chemical fingerprint. And that fingerprint was evidence of a crime the models did not allow: accelerated chemical enrichment. These three mechanisms, redshift, lensing, and spectroscopy, form Webb's basic toolkit. One tells it where to look, another how to see better, and the third how to understand what it sees. Together, they are painting an unprecedented picture of the earliest epochs of the universe. And this picture is full of inconsistencies. But these inconsistencies are not a failure of theory. On the contrary, they are the birth pangs of a new theory. Because Webb's data is also beginning to test other, more speculative mechanisms that could explain these anomalies. For example, the efficiency of star formation in the early universe. Perhaps the first stars were converting gas into stars much more efficiently than we thought. Or perhaps the growth mechanisms of black holes were completely different. But beyond all these technical details, Webb is measuring something else, and this measurement may be deepening the biggest tension, the biggest crisis in modern cosmology, because that measurement is about the expansion rate of the universe itself, and that rate is the key that either connects everything or tears everything apart, and that rate was a puzzle that was tearing everything apart. This puzzle is called the Hubble tension. This crisis at the heart of modern cosmology arises from the fact that the two primary methods for measuring the current expansion rate of the universe stubbornly give different results. This is like measuring the same person's height with two different Schiartz reliable tape measures and finding a difference that cannot be reconciled. The first method uses the cosmic microwave background radiation, the universe's baby picture. And by analyzing the patterns in this radiation, physicists can calculate the expansion rate in the early universe and, using known physics, predict its value today. This method consistently gives a value of about 67 kilometers per second per megaparsec. This means a galaxy about 3.26 million light years away from us, is receding at a speed of 67 kilometers per second. But the second method uses a technique called the distance ladder. In this technique, nearby objects with precisely known distances are used to calibrate the distances of more distant objects. The most reliable rungs on this ladder are Cepheid variable stars, whose brightness changes in a specific pattern, and Type 1a supernova explosions, which always reach roughly the same peak brightness. But astronomers using this method consistently find a higher value, around 73 kilometers per second per megaparsec. Webb became directly involved in this debate because its sharp vision could make brightness measurements of Cepheid stars more precisely than ever before. If the tension was due to a measurement error, like nearby stars blurring the image, Webb would have revealed it, but it didn't. On the contrary, Webb's observations confirmed and strengthened the value of 73. So, the tension is no longer a suspicion, it's a fact. And this fact means that if the universe is expanding faster, its age is slightly younger than we thought. This makes the early galaxy problem even worse, because it leaves even less time to build those massive structures. So, some theorists turn their eyes to the most mysterious and dominant component of the Standard Model: dark matter. The dark matter in the Standard Model is called cold. The word cold here doesn't refer to its temperature, but to the speed of its particles. Cold, dark matter particles move slowly relative to the speed of light. So, gravity can easily gather them into dense clumps. This model explains the large-scale structure of the universe and the fluctuations in the cosmic microwave background with extraordinary precision. But Webb's data contradicts the predictions this model makes for the early universe. Because cold dark matter says that structures should grow slowly and hierarchically. That is, from the bottom up. But Webb seems to be finding the opposite: large, organized structures appearing very early on. This has led some theorists to seriously reconsider alternatives like hot dark matter. Hot dark matter particles move faster and resist clumping on small scales. This produces different predictions for how structures form in the early universe. Or perhaps dark matter is not a single type. Maybe there are multiple types with different properties. Or maybe dark matter interacts with our matter, or with itself, in ways we don't yet know. Webb's observations showing that structures in the early universe are more advanced than expected are therefore not just a puzzle, but also a measurement. They are telling us something about the small-scale behavior of dark matter. And that behavior doesn't fit the simple and elegant picture of the Standard Model. And as if that weren't enough, there is also dark energy, this mysterious force. Discovered in the late 20th century, showed that the expansion of the universe is not slowing down, but is actually accelerating. In the Standard Model, dark energy is treated as a cosmological constant, a constant energy density permanently woven into the fabric of space. It doesn't dilute or strengthen as it expands, it just pushes. But some analyses of distant starbursts at various cosmic distances by Webb are pointing to data more consistent with a dark energy that is not constant over time. In some analyses, the signal points to a dark energy that was stronger in the early universe and has weakened since. In others, the data points to a value that fluctuates in ways the cosmological constant does not allow. The consequences of a changing dark energy would be extraordinary, because it would likely require changes in general relativity itself or the introduction of new fields in physics. Researchers are extremely cautious about these results because the statistical significance is not yet at the threshold required to make a definitive claim, but the hint is there, and this hint, combined with the Hubble tension, the early galaxy problem, and all the other places where the standard model is under pressure, paints a picture of a cosmological framework under pressure from an unusual number of directions: redshift, lensing, spectroscopy, the Hubble tension, the dark matter enigma, and that unsettling hint that dark energy might be variable. All these technical mechanisms and problems tell one big story. Our understanding of how the universe works at the most fundamental level is incomplete. But this is not a failure. This is science itself, because each of these anomalies is nature's way of telling us, look here, there is something you don't understand here. And now, it's time to bring all these anomalies together and look at the unified picture that Webb has revealed. That climax. Because when these pieces come together, the resulting picture is far more shocking than the sum of its individual parts. With the data we now have, we are ready to ask the most disturbing questions. What if it's not the models themselves that are wrong, but a fundamental assumption upon which the models are built? What if the fabric of the universe is more? And now, the real storm breaks. All those technical details, all those theoretical cracks, they were just the foreshocks of the biggest cosmic earthquake we have ever seen. But because Webb didn't just question the models, Webb photographed but one by one. The very things the models said were impossible, they were real. The images were there, and every single pixel in those images was a piece of evidence, dynamiting the foundations of cosmology. Now, we are pushing the tempo to the maximum, because we are no longer talking about theories, but about the history-making, mind-bending discoveries themselves that shattered those theories. Fasten your seatbelts, because we are now speeding towards the edge of science, into the heart of the unknown, the first shockwave, colliding galaxies, but where they shouldn't be. In the first billion years of cosmic history, the universe was smaller and denser, but it was also expanding at a very high rate. So, galaxies were being carried away from each other, according to the standard model. The probability of direct collision and merger at that time was extremely low. Galaxies were supposed to grow mostly by slowly accreting the gas around them. But Webb looked there, and it found a scene of absolute carnage. For the first time in history, merging galaxy systems were clearly imaged at distances corresponding to the first billion years of the universe, and at a frequency many times higher than expected. The images showed tidal tails of stars and gas, torn from one galaxy to another by gravitational interaction. There were bridges of matter stretching towards each other. There were disks warped by the impact of the collision. These were the undeniable signatures of close gravitational encounters. Sad because this showed that the distribution of the first galaxies was much denser than the models allowed. A denser beginning meant more collisions. More collisions meant faster growth. This connected directly to the dark matter distribution problem and the early cosmic web problem. And one observation took everything even further. Webb found a merging system at that distance, containing enough stellar mass to rival a large modern galaxy. Finding an event of this scale in the first billion years of the universe was completely outside the predictive range of any currently used simulation. The scientific world was shaken. Because this wasn't just an anomaly. This was proof that the most fundamental engine of galaxy evolution, mergers, multits, was running at full throttle billions of years earlier than we thought. But this was just the beginning. The second blow, reionization, but like a storm. The standard model said that the process of clearing the fog of neutral hydrogen that enveloped the universe was slow, gradual, and relatively smooth. The process was supposed to be complete about 1 billion years after the Big Bang. Webb looked at that period of the universe from different directions, and for the first time in history, it showed that the process of reionization was incredibly patchy and chaotic. This was a revolution. Because, in some directions, there were signatures showing that the neutral hydrogen fog had lingered for hundreds of millions of years longer than expected. But in other directions, the gas appeared to have been cleared incredibly early, long before the standard timeline allowed. This was like some corners of a room lighting up instantly, while other corners remained dark for hours. What could produce this level of spatial variability? The answer was concentration. Some regions of the early universe were apparently far ahead of schedule, containing unusually dense asteroids, powerful populations of early galaxies that emitted enough ultraviolet radiation to ionize the vast volumes of space around them. These galaxies were opening up giant bubbles of transparency in the neutral fog. This was a much more violent and irregular cosmos, replacing the smooth, orderly picture predicted by the models. Scientists were in shock, because this patchy structure meant that different regions of the universe were evolving at different times, all at different speeds. This was a starting condition that affected all subsequent cosmic evolution, and that condition did not fit any model we knew. Every single pixel in those images was a piece of evidence, dynamiting the foundations of cosmology. Now, we are pushing the tempo to the maximum, because we are no longer talking about theories, but about the history-making, mind-bending discoveries themselves that shattered those theories. Fasten your seatbelts, because we are now speeding towards the edge of science, into the heart of the unknown. The first shockwave, colliding galaxies, but where they shouldn't be. In the first billion years of cosmic history, the universe was smaller and denser, but it was also expanding at a very high rate. So, galaxies were being carried away from each other, according to the standard model. The probability of direct collision and merger at that time was extremely low. Galaxies were supposed to grow mostly by slowly accreting the gas around them. But Webb looked there, and it found a scene of absolute carnage. For the first time in history, merging galaxy systems were clearly imaged at distances corresponding to the first billion years of the universe, and at a frequency many times higher than expected. The images showed tidal tails of stars and gas, torn from one galaxy to another by gravitational interaction. There were bridges of matter stretching towards each other. There were disks warped by the impact of the collision. These were the undeniable signatures of close gravitational encounters. Sad because this showed that the distribution of the first galaxies was much denser than the models allowed. A denser beginning meant more collisions. More collisions meant faster growth. This connected directly to the dark matter distribution problem and the early cosmic web problem. And one observation took everything even further. Webb found a merging system at that distance, containing enough stellar mass to rival a large modern galaxy. Finding an event of this scale in the first billion years of the universe was completely outside the predictive range of any currently used simulation. The scientific world was shaken. Because this wasn't just an anomaly. This was proof that the most fundamental engine of galaxy evolution, mergers, multits, was running at full throttle billions of years earlier than we thought. But this was just the beginning. The second blow, reionization, but like a storm. The standard model said that the process of clearing the fog of neutral hydrogen that enveloped the universe was slow, gradual, and relatively smooth. The process was supposed to be complete about 1 billion years after the Big Bang. Webb looked at that period of the universe from different directions, and for the first time in history, it showed that the process of reionization was incredibly patchy and chaotic. This was a revolution. Because, in some directions, there were signatures showing that the neutral hydrogen fog had lingered for hundreds of millions of years longer than expected. But in other directions, the gas appeared to have been cleared incredibly early, long before the standard timeline allowed. This was like some corners of a room lighting up instantly, while other corners remained dark for hours. What could produce this level of spatial variability? The answer was concentration. Some regions of the early universe were apparently far ahead of schedule, containing unusually dense asteroids, powerful populations of early galaxies that emitted enough ultraviolet radiation to ionize the vast volumes of space around them. These galaxies were opening up giant bubbles of transparency in the neutral fog. This was a much more violent and irregular cosmos, replacing the smooth, orderly picture predicted by the models. Scientists were in shock, because this patchy structure meant that different regions of the universe were evolving at different times, all at different speeds. This was a starting condition that affected all subsequent cosmic evolution, and that condition did not fit any model we knew. And then IT came, the black hole at the edge of history. It was impossible. But it was there. Supermassive black holes were thought to grow through a slow feeding process over billions of years. So, finding a black hole of tens or even hundreds of millions of solar masses in the first billion years of the universe was seen as physically impossible. But in 2023, Webb did exactly that, at the center of a galaxy from less than 1 billion years after the Big Bang. It detected a black hole with a mass of tens of millions of times that of the Sun. This was a record-breaking discovery. This was one of the largest black holes ever found at such an early epoch. To build this monster in such a short time, according to the known laws of physics, it would have had to devour matter non-stop, at its maximum feeding rate, called the Eddington limit, for every single moment of its existence. This is like a person eating the absolute maximum amount of food they physically can, every second from the moment they are born, without ever pausing. An almost impossible scenario. This discovery made headlines in all scientific journals because it pointed to one of two possibilities. Either the black hole seeds were formed by exotic mechanisms like direct collapse, much larger than those formed by the collapse of a star, or the early universe created super-efficient feeding conditions that we do not yet understand, allowing black holes to exceed this physical speed limit. Both options meant new physics, and Webb's findings demanding this new physics were coming one after another. But the biggest earthquake had not yet arrived. Those 6 galaxies, the cosmic dinosaurs, That paper published in early 2023. That was the moment everything changed. 6 massive galaxies found in Webb's data. What made them special wasn't just their age, not just that they belonged to the first 500 to 700 million years of the universe. What made them impossible was their mass. One had a mass of 100 billion times that of the Sun. This is a value close to the current mass of our Milky Way galaxy. But it was this size when the universe was only 3% of its current age. These 6 galaxies literally shattered the total amount of stellar mass that should have been in the universe at that time. The stellar mass function. They contained 100 times, and by some calculations, even 1,000 times. More mass than the predicted amount. The famous quote from the paper's lead author, Carl Erica Nelson, summarized the situation. This is like finding dinosaurs in the Precambrian era. This wasn't just a surprise. This meant that the timeline itself might be fundamentally wrong. When the paper was published, the scientific world was virtually split in two. Some argued that it must be a measurement error, but in the following weeks, more than a dozen independent teams downloaded the same data and did their own analyses. Some found slightly lower mass estimates, but none of them found that the objects disappeared entirely. Those dinosaurs were real, and they were screaming that the cosmology books needed to be rewritten. These 4 great shocks, collisions, the Ryanization storm, the impossible black hole, and the cosmic dinosaurs, each one was a revolution in itself. But jammed together, they formed a coherent pattern. A pattern showing that in every area of the early universe, in every process, in every structure, everything was happening much faster, much bigger, and much earlier than expected. So, what is the meaning of this pattern? When all these pieces come together, what do they tell us about the universe? Is this just a situation where a few models need to be adjusted? Or is it something much more fundamental? Because there was another anomaly hidden in Webb's data, perhaps the deepest of them all. An anomaly related to the very fabric of the universe itself. And that anomaly could be the key that either connects everything or shatters everything forever. Because that key was suggesting that one of the most fundamental constants of the cosmos might not be constant at all, and that key was whispering that one of the most fundamental constants of the cosmos might not be constant at all. This was the deepest, most unsettling clue yet, because this wasn't just about how a galaxy forms. This was about the nature of the universe itself. Yet all these anomalies, this accelerated evolution, these impossible structures, they might all be pointing to a single possibility, that the cold dark matter model, one of the main pillars of the standard cosmological model, is wrong, at least in the early universe. So, Webb wasn't just testing distant galaxies, it was also testing the very nature of dark matter, and the results were heralding a revolution. The 5th shock, the cosmic web, but a web woven much earlier than expected. The standard cold dark matter model predicts that the largest structure in the universe, the cosmic web, the vast network of filaments connecting galaxy clusters, should form slowly over time. But Webb demolished this prediction, and for the first time in history, it found an array of galaxies aligned along a fully developed filament-like structure at a distance corresponding to just 800 million years after the Big Bang. This was a record-breaking structure. The galaxies were arranged in a pattern you would expect to see in a much older, much more developed cosmic web. If this structure is real, and multiple teams have found consistent signals, Then gravity was working faster in the early universe than any current simulation predicts. How could this be possible? Either there was more matter than the models accounted for, or the matter was distributed in a way that enhanced gravitational collapse, or there was something different about the expansion history of the very early universe than we assumed. The scientific world was shaken by this finding, was because this wasn't just a problem of a few galaxies forming early. This was evidence that the very skeleton that forms those galaxies, the dark matter structure itself, was in place billions of years earlier than the models allowed. This meant the entire structure could be fundamentally flawed. And then the sixth wave came, gravitational lensing, but the numbers were wrong. Gravitational lensing is the most direct way to see dark matter. And Webb's observations in this field produced results that did not exactly match the predictions of the standard model. In several galaxy clusters, the dark matter distribution inferred from the geometry and strength of the lensing did not agree with what simulations predicted for clusters of equivalent size and age, and in some cases, the dark matter appeared more concentrated in the cluster centers than the models allowed. In others, it seemed a bit more smoothly distributed than simulations predicted. Scientists approached these inconsistencies with appropriate caution, because systematic errors could affect these measurements. But the pattern itself was unsettling. Multiple clusters, multiple analysis methods, multiple independent research groups, all were finding consistent deviations from standard predictions in the same direction. A dark matter that clumps differently than expected could provide a potential mechanism for the rapid galaxy formation observed by Webb. It could explain the early developed cosmic web. It could connect the early galaxy problem to the structure formation problem with a single fundamental cause. And scientists held their breath, because if this cause was real, the galaxies tearing each other apart at the edge of the observable universe were about to make the puzzle much more specific. This was a direct challenge to one of the most sacred beliefs in cosmology, the simplicity and success of cold, dark matter. And finally, the seventh seal was broken. The Hubble tension, but no longer a tension, a crisis. Webb entered this debate as the final arbiter, and the verdict it delivered was one no one wanted to hear. Observations of Cepheid, variable stars in distant galaxies, confirmed the higher value for the universe's expansion rate, about 73 kilometers per second per megaparsec. With greater precision than any previous telescope, the last hopes that the tension was a measurement error thus evaporated. The crisis was official. There was a fundamental discrepancy between early universe measurements, the cosmic microwave background, and late universe measurements, Webb's distance ladder. How could this be possible? This could mean either that there is new physics that changes the expansion history between the early and late universe, or that the theory of general relativity itself is incomplete on cosmological scales. Both options mean a paradigm shift. Because this situation exacerbates all of Webb's other findings. A faster expansion means a younger universe. A younger universe means even less time to build those impossible galaxies and black holes. This was one of the biggest deadlocks science had seen in decades. And Webb, instead of resolving that deadlock, deepened it. So, here is the big picture: colliding galaxies, a stormy reionization, impossible black holes, cosmic dinosaurs, an early woven cosmic web, incorrectly clumping dark matter, and an unresolved, a deepening Hubble crisis. These 7 major discoveries are no longer holes to be patched. They are the cornerstones upon which a new universe is being built on top of the old model. What Webb has shown us is not just a few anomalies. Webb has shown us a brand new cosmos, a cosmos that is faster, more violent, more complex, and became active much earlier than we thought. But now, after this dizzying pace, it's time to pause and take a breath, to stand in the midst of all this data, these shocks, these revolutions, and ask the most fundamental question. Where is our place in all this cosmic drama? What does this new universe mean for us? It's because the deepest consequence of these discoveries may not be hidden in numbers or graphs, but in what we see when we look in the mirror. This is a moment of redefining humanity's place in the universe, and that definition comes from a place we never expected. But now, it is time to stop and think. In the midst of these dizzying discoveries, these cosmic revolutions, it's time to take a breath for a moment and face the most fundamental question. All these galaxies, these black holes, these seemingly infinite structures, what do they all mean for us? The James Webb Space Telescope didn't just show us a new universe, it also made us question our place within that universe. Because the deepest truth that Webb has revealed is perhaps not hidden in numbers or graphs. What sieht Chinesen but in the most fundamental paradoxes of the human condition. Now, let us embark on a slow and deep journey into those paradoxes, into the heart of our own existence. The first paradox is about scale. On one hand, there is a universe of incomprehensible size that Webb has shown us. The observable universe itself is roughly 93 billion light-years across. It is estimated to contain at least 2 trillion galaxies, each containing hundreds of billions of stars. Webb showed that one of these galaxies, even when the universe itself was just 300 million years old, had already reached hundreds of billions of solar masses. But on the other hand, within this massive stage, there is you, a carbon-based being, standing on the surface of this planet, at about 1.7 meters tall. It is almost impossible to hold these two scales in your mind at the same time. On one side, trillions of galaxies. On the other, a single consciousness. How is this possible? While we are not even a speck in this cosmic ocean, how can we be aware of this ocean? There is a tragic side to this situation, because those distances are forever unreachable for us, even the nearest star system. Proxima Centauri is a journey of about 6,300 years with our fastest current spacecraft. Reaching those first galaxies that Webb looked at is unimaginable. We will never visit them. We will not be able to touch the light of those ancient stars. Physically, we are trapped on this planet, in this solar system. This is a deep sense of cosmic loneliness. It's like the universe knocking on our door, but knowing we can never go inside. We are beings who watch an infinite landscape from behind a glass, but can never step into that landscape. But there is also an incredibly beautiful side to this paradox. Because, yes, we cannot physically go to those galaxies, but our minds can. The James Webb Telescope is exactly that. It is an extension of the human mind, of human curiosity, reaching into space. The equations that built that telescope, the algorithms that analyze that data, the theories that interpret those results, all are products of the brain inside that 1.7 meter body. The universe may be vast, but we may be the only part of that vast universe that can understand it, that can solve its laws, and that can ask questions about its origin. But we are the universe, aware of the universe. So, yes, you are a small drop in this cosmic ocean, but you are also the eye through which that ocean beholds itself. And this turns our smallness not into a weakness, but into a unique privilege. The second paradox is about time. Webb takes us to the beginning of time, 13.8 billion years ago. It shows us the infancy of the universe, the birth of the first stars, the formation of the first galaxies. It reminds us that we are part of a cosmic saga that has lasted for billions of years. But on the other hand, there is our own time. The average human lifespan is about 80 years. This is less than a blink of an eye on the cosmic calendar. If we were to compress the 13.8 billion year history of the universe into a single year, all of recorded human history would correspond to the last 14 seconds of that year. Your entire life would be nothing more than a momentary flash within the last second of that year. How can such a fleeting existence be aware of such an eternal story? The tragic truth of this is our transience. We are in this universe for just a moment. We are born, we live, and we die. We were not here when those first galaxies were born. We will not be here billions of years from now, when the last stars go out. Our story is an almost invisible footnote in the infinite flow of cosmic time. Those ancient galaxies that Webb shows us were there billions of years before our species existed, and will likely be there billions of years after. This is the moment when humanity confronts its own insignificance. As the giant river of time flows by, we are only allowed to stand on the riverbank and look at the water for a moment. But this transience also has a profound beauty, because maybe that moment is enough. Maybe what matters is not how long we live, but what we become aware of in that brief moment. We have coincided with that unique moment in the history of the universe when a life form intelligent enough to see its own past emerged. We are the generation that could build a tool like Webb and capture the light of the Big Bang. This is an incredible stroke of luck. Countless life forms that have existed for billions of years, if any, could not do this. Maybe life forms billions of years from now will not be able to do it either. But we can, right now. So, you exist for only a second on that cosmic calendar, but that second is the second when the universe reveals its own secrets, and to be a witness to that moment may be more meaningful than living forever. The third paradox is about knowledge and mystery. James Webb is the most powerful information-gathering tool in human history. It has shown us galaxies, stars, and chemical signatures we have never seen before. It has shaken the decades-long dominance of the Standard Model and proven to us that the universe is far more complex than we thought. Every new image, every new dataset, pushes the boundaries of our knowledge even further. But at the same time, for every mystery it solves, it replaces it with dozens of new mysteries that are much larger and deeper. Webb was built to give us answers, but the greatest thing it has done is to teach us to ask new questions we couldn't even have imagined asking before. How did early galaxies grow so fast? What is dark matter really? Why does dark energy exist? Every answer leads to a why question. How can this be? How can our ignorance become even more apparent as our knowledge increases? The tragic side of this is that perhaps we will never reach the final answers. Perhaps the universe is, by its very nature, too complex for the human mind to fully comprehend. Perhaps each new layer of discovery is like an infinite onion, with an even more complex layer underneath. This is like running towards a horizon. No matter how fast you run, The horizon always stays the same distance from you. This is a humbling lesson for us in the pursuit of knowledge. So perhaps our purpose is not to know everything, but to stand in awe before the infinity of what we do not know. But this infinite mystery also has a revitalizing beauty. Because if we knew everything, what would be left to discover? If the answers to all questions were found, what would be the point of waking up in the morning and pointing the telescope to a new target? What Webb has shown us is that the universe is not a boring place. It is a dynamic, living place that constantly surprises us, shatters our assumptions, yes, and invites us to learn more. So, science itself is not a destination, but a journey. And that journey gains meaning more from questions than from answers. You are a part of this journey, and every day, with every why, you ask, with everything you wonder about, you are helping to peel back one more layer of that infinite onion. And perhaps the real treasure is not in the center of the onion, but in the act of peeling it itself. These three great paradoxes: scale, time, and knowledge. They are all reflections of the new universe that Webb has shown us, and they all bring us back to the same fundamental truth. But hidden within these paradoxes is another, more personal, more direct question. And that question is about how the chemistry of the universe and the chemistry of our own bodies are inextricably linked. Because the elements that Webb found in those most distant galaxies are not just astronomical data points. They are our very existence. And when we understand this connection, our relationship with the universe, and when we understand this connection, our relationship with the universe changes forever. Because those chemical fingerprints that Webb found in those most distant galaxies are not just astronomical data points. They are our origin story. Oxygen, carbon, iron. These elements were forged in the hearts of those ancient stars billions of years ago, scattered into space by supernova explosions, and after a journey of generations, became the raw material that makes up our planet, our bodies. Today, this is the fourth fight, and perhaps most personal paradox: strangeness and belonging. On one hand, the universe that Webb shows is an incredibly strange and hostile place. A vacuum of negative 270 degrees, intense radiation storms, and black holes that swallow everything. It is not a place designed for delicate, Jatsachi, carbon-based life forms like us. We are an anomaly by the standards of this universe. We are exiles living on a small, sheltered island in this cosmic ocean, blessed by a protective atmosphere, liquid water, and a stable star. The universe outside is a deadly desert for us. This leads us to a sense of strangeness, as if we are not a major part of the universe, just a cosmic accident, surviving by chance. The tragic truth of this is that this strangeness is true to some extent. The vast majority of the universe is an extremely hostile environment for life. Those first galaxies that Webb looked at were violent and chaotic places where the complex chemistry and stable conditions necessary for our existence had not yet emerged. Also, when we look at the rest of the universe, we see not a mirror, but an other that operates by rules we cannot even imagine. Very different from us. This can create a sense of not belonging, as if we have no home in this universe. But the most powerful and beautiful truth of this paradox is that the exact opposite is also true. Because, yes, the universe may seem alien to us, but we are made of it. The iron atom circulating in your blood came from the heart of a star that exploded billions of years ago. The oxygen you breathe was once created inside a star similar to those in the ancient galaxies Webb now looks at. The calcium in your bones made a journey of billions of years through the depths of space. We are not alien to the universe. We are the universe. Like we are the part of the universe that can know itself, feel itself, and marvel at its own beauty. So, you may feel like a stranger in this universe, but you should also know that you are the lost child of the universe, carrying stardust in your veins. And perhaps home is not a specific place in space, but the moment we understand this deep connection. And the final paradox is about silence and message. For decades, we have been listening to the sky. We use giant radio telescopes in the hope of a signal, a message from other intelligent life forms. But so far, all we have found is a great silence. The universe appears to be silent in terms of intelligent life. This brings up the famous question known as the Fermi paradox. If the universe is so large and old, why are we alone? Why don't we see evidence of others? This cosmic silence is an eerie feeling that makes one question humanity's place in the universe. The tragic side of this silence is that we may have to face the fact that we are indeed alone. Perhaps intelligent life is an incredibly rare phenomenon. Perhaps among countless planets, we are the only species to have reached this level of complexity. This places an incredible weight on our shoulders, because this could mean that all the hopes, all the dreams, and all the consciousness of the universe depend on a fragile species on this small, pale blue dot. If we fail, the universe's chance to understand itself may be lost forever. This is a responsibility of unimaginable magnitude. But this silence may also have a different, deeper message, because perhaps the universe is not speaking to us in words, and perhaps the message of the universe is hidden not in radio signals, but in physics itself, in the light of the stars, in the structure of galaxies. Every image that Webb sends us is a part of that message. That message tells us that the universe is orderly, predictable, and above all, understandable. That message shows us that the same fundamental laws apply in a galaxy 13 billion light-years away as they do in our laboratories. Perhaps the greatest message the universe is sending us is this: you are not alone, because you are a part of me, and you can understand me. So, you may feel a sense of loneliness in that cosmic silence, but you can also think that every single photon that Webb captures is a personal letter sent to you by the universe. And by reading those letters, we are having our deepest dialogue with the universe. At the end of all these discoveries, this dizzying journey, we may feel like those scientists in the control room. On one hand, a sense of smallness and sadness that comes from seeing how big, how old it holds, and how indifferent the universe is. On the other hand, an incredible sense of power and wonder that comes from being a being that can understand all this, that is a part of this giant structure, and that can solve its secrets. Perhaps both feelings are true. Perhaps being human is to stand right at the intersection of these two feelings: the tragedy of being a cosmic orphan and the miracle of being made of stars. We are now approaching the end of our journey. We have seen both the shocking discoveries and the deep philosophical reflections of the new universe that Webb has shown us. We have navigated the paradoxes of scale, time, knowledge, belonging, and silence. We now know that we are both insignificant and priceless, both transient and witnesses to eternity, both alone and an inseparable whole with the universe. The James Webb Space Telescope did not just present us with a picture of the universe. It held up a mirror for us to look at ourselves. And what we see in that mirror is complex, contradictory, but above all, full of hope. Now, it is time to bring together everything we have learned on this journey and look one last time at the ultimate meaning of our place in this new cosmos. Because Webb's greatest legacy may not be the discoveries it will find in the future, but the infinite curiosity and wonder it has awakened in us today. And that feeling is the very thing that makes us human. In this journey, we saw how vast and complex the universe is. But there is something I didn't tell you. What if this three-dimensional reality is just an illusion? Written on a two-dimensional surface? Could the universe be a hologram? In our next journey, we will question reality itself. We will dive into the depths of this mind-bending theory for which scientists are searching for evidence. Are you ready?